Yeah, or if we lived somewhere about 8 years ago that was like had radon in the basement or something.
Oh yeah.
That's have to be.
Did you hear Floor's? Did you go to the horizon?
No, because actually that's what
So, she was
Oh, did they? Yeah, that's a good sign. Yeah. Yeah, that's not good. There's a certain, there's different paths.
Oh no, that is like these things.
Or no. Yeah, there was a path. But we'll see. It was great.
Okay, let's get started. Good morning, everyone. Welcome to the public portion of Floor Broekgaarden's thesis defense. This is the first of 8 PhD thesis defenses over the next 2.5 weeks, so buckle up. Floor's thesis, titled Gravitational-Wave Paleontology, a new frontier to probe massive binary stars across cosmic history, is the culmination of nearly 4 years of research in which Floor has explored the question of how to use gravitational wave events, the present-day fossils, to study the formation and evolution of massive star binaries, the original living animals. Hence, gravitational wave paleontology. Until a few years ago, the study of how gravitational wave compact object binaries form using population synthesis modeling was focused on making very basic predictions, such as rates and mass distributions. But starting in 2015, with the actual first detection of gravitational wave events, including black hole binaries, neutron star binaries, and Floor's personal favorites, black hole neutron star binaries, this field is now shifting focus from basic predictions to interpretation and model constraints. And boy, are there a lot of parameters and processes to constrain, as you'll hear about today. Things like binary initial conditions, mass transfer episodes, stellar evolution, common envelope processes, supernova explosions and kicks, remnant messes, etc., etc., etc. But with the rapid growth of gravitational wave detections and better facilities that are finding these events further and further away, there is actually hope to delineate this process, and this is what Floor is going to tell us about today. Now, as all of you know, Floor's time at the CFA has also been marked by her unusual commitment to an impact on improving the climate, professionalism, and support for early career astronomers. Many of you have participated in and contributed to the series on early career astronomer workshops that Floor has organized, as well as other events. Indeed, I would say that Floor is the proof that one can be an excellent scientist, a supportive and generous colleague, and a dedicated citizen of astronomy all at the same time. The impact of Floor's thesis has been recognized with a NASA Finesse Fellowship and recently a Harvard Horizons Fellowship. And I urge those of you who haven't had a chance to watch that talk to go online and look at the recording. It was really phenomenal. Starting next fall, Floor is going to be a Simon Society of Fellows postdoc at Columbia University and the CCA. And for those who have not heard, Floor was also recently offered a faculty position at Johns Hopkins University. Floor, it's been a real pleasure working with you for the past 4 years. I learned a lot from you as a scientist and as an advisor. And so the floor is now yours to tell us about it.
I've not heard that. Thank you all for coming to my PhD defense talk. It's definitely an interesting journey, and
the remaining topic of my thesis focused around gravitational wave paleontology, as Ido mentioned. And the central topic is kind of that throughout my thesis, massive stars for me are the dinosaurs of our universe. And as I'll show you, like similarly to how paleontologists use like fossils to study how dinosaurs lived, in my thesis, I use the fossils of massive stars, collisions of black holes and their gravitational waves, to understand how these massive stars formed, lived, and died in the past. But first things first, so compared to our sun shown here, massive stars are these stars that can be 10 to 200 times as massive. They are short-lived. They live fast and die young, so often they have lifetimes that are 1,000 times shorter than our own sun. And they're very rare, so the initial mass function tells us that only 1 in 1,000 stars is typically formed as a massive stars. And this is why it's so challenging to observe many of them and study them. And this is true for our Milky Way, where you often rely on very, very expensive observations, for instance, with the Hubble telescope of these massive stars in nearby environments, but often obscured by dust, and still very, very expensive to observe many. And it's even more difficult to find them in more distant environments, such as low metallicity galaxies much further away, where it's almost impossible, and we often have to rely on like integrated light of galaxies. And so overall, very little is known about these massive stars. But one thing we do know is that they play a pivotal role in shaping our universe through all these different processes. So they, for instance, trigger and star formation. They provide a lot of feedback. They often are the dominant source of light from these early galaxies. And for example, they produce all the oxygen that we breathe here on Earth. Another cool thing is that these massive stars, they often form in pairs, binaries. And the life of these massive stars in a pair can be drastically different from that of a single star. They can interact and exchange mass. And these massive stars, when they end their lives, they actually go supernova and can form a black hole in these bright explosions. And so if both of them explode and can stay together as black holes, you might form a pair of black holes, here shown as marbles, since it's really difficult to visualize black holes, and I didn't have the budget of Interstellar. And these black holes, they over time spiral in and eventually collide, forming a slightly more massive black hole. And as of 2015, we can now observe these collisions. And so this raised the question from scientists to ask, if we can observe these black hole collisions, can we use this as fossil to study how these massive stars formed, lived, and died in the past? And so this question is central to my thesis and basically opens this new frontier that we call Gravitational-Wave Paleontology, studying stars in the past from their fossils as black hole collisions. Okay, so how does this work? Well, all around us, there are these pairs of black holes that occasionally collide, during which they unleash these bursts of gravitational waves that travel through space and can reach us over millions and millions of years, eventually here on Earth, where they squeeze and stretch Earth itself, here vastly exaggerated. And these stretches can be picked up here in the US, for instance, with laser interferometers that can kind of find and make an interference pattern from these like wiggles in space. But they're super tiny. And so what LIGO finds, for instance, is something that looks like this, a chirp. And from these observations, scientists can infer the properties of these black holes, such as their masses that leave different imprints in these chirps. And there's something really cool about these black hole collisions for studying massive stars. And that is that they actually probe our entire universe. And to give an idea of that, here's a picture of like our entire universe in one image, where here we started with the Big Bang, then the first stars formed, and then over millions and billions of years, we eventually reach at the present day. Now, these stars that form black hole collisions are very special, because maybe they form these black hole pairs in just a few million years, nothing in the lifetime of the universe. It can actually take billions and billions and billions of years before the black holes eventually collide and form the gravitational wave source. And sometimes it might go faster, and sometimes it might be hundreds of millions of years, sometimes hundreds of billions of years. But this means that the gravitational wave sources that we're seeing today, even the local ones, actually probe massive stars to deep into the universe and deep into our past, possibly as far away as when the first stars were formed, to the edge of our observable universe. Pretty cool. At the same time, if we go back to this picture, these black hole collisions don't directly leave imprints and provide us information of the stars themselves. So in practice, we have to forward model how stars live and how they form gravitational wave sources. Compare it to how maybe fossils don't directly inform you about whether a dinosaur has feathers, but we can study how feathers of a dinosaur leave imprints on the fossils today. And so in practice, throughout my PhD, I've actually spent a lot of time on doing those stellar evolution calculations. And in practice, it looks something like this, here animated, where as theorists, we put in hypothetical pairs of stars in this factory or code, for instance, called COMPASS that I worked on. And this code will then determine whether such a pair of stars with different masses can form successfully a gravitational wave source, a black hole pair that stays together and collides. And so these are called population synthesis simulations for stellar evolution. And so with a bunch of collaborators all over the world, some of them are here, Reinhold and Lieke, we worked on this code called COMPASS to do these stellar evolution calculations, which is basically this factory. And so in practice, this looks something like this, a big GitHub page where all the code, C++, Python is hosted that can calculate all these calculations and stellar evolutions for these stars. And so during my PhD, we, for instance, had the first public release of this code in April of 2020. This was still in the pandemic, so we had to do the party over Zoom. And this thereby presented the only basically second public code of these stellar evolution factories. And this is the only one that focused on basically gravitational wave sources of binary black holes, black hole neutron stars, and binary neutron stars. And it was really optimized to be very efficient, so be very fast. And another thing that I did during my PhD was actually very fun, was to actually lead with some others one of the methods papers of this code, where many, many people contributed, and that was published in 2022. But that being said, you might say, okay, this sounds problem solved. We now have this stellar evolution code, COMPASS, we're done, right? End of PhD. Well, not so easy, because as I'll show, actually the main focus of my PhD thesis is that this is not as easy as it maybe sounds. And this is because of the so-called uncertainty challenge. And this is that doing these calculations, there are 4 key barriers, hurdles, that we have to overcome that present a challenge, which all come from that these codes have many, many uncertainties underlying the code, like in stellar evolution prescriptions, that make this so expensive and to date not possible. And I'll go into detail what these are. So the first one is that the formation channels of these gravitational wave sources are uncertain. So in practice, we don't really know how these gravitational wave collisions formed. And so, for example, they might form from pairs of stars that form in isolation as a binary, as I showed. And so in this case, here's an example where you maybe start with 2 stars. Then one evolves and can exchange mass to the companion star. Eventually, it leaves behind a helium star and a star, and it goes supernova, forming the first compact object in a companion with a star. The system might evolve further. Then also, again, the second star might evolve and now engage in mass transfer, but this time it might actually be unstable, leading to this so-called common envelope phase, where now the compact object is engulfed in this envelope of the companion star, and drag leads the system to spiral in. And so what you end up with is this very close black hole strip star pair that's much, much more close together. The other star might also go supernovae, and then you can form, for instance, indeed my favorite, a black hole neutron star compact object binary. That then, if it's close enough together, can spiral in over time and form a gravitational wave source that we see today. This is one formation channel, But as you saw, there's many, many others. For example, they might form from these population 3 stars, very low metallicity stars early in the universe that can stay small. They might form chemically homogeneous, where they also are formed so close together that they rapidly rotate and they also can stay small. Or with a third companion that can help the system get closer together. And then there's this whole other class of formation channels, where now instead you actually have many stars and compact objects in dense stellar environments, 1,000,000 times more dense than in the other case. And now these compact objects and star can actually interact through 3-body interactions like this, and eventually kick out one of the stars and in that way get closer together. And then there's a whole other category, such as maybe there's stellar flybys that help the system get close together, or maybe they're actually formed primordial. And there are many, many combinations. You might actually have triples or binaries in these dense stellar environments and so on and so on. So you start seeing that this becomes very, very, very complicated. And so in practice, we don't just have to do one simulation. We actually have to redo our simulation for all these different formation pathways to understand what kind of gravitational wave sources they leave behind, presenting our first challenge in this picture. The second challenge is that we don't really know what the initial conditions of these stars are to begin with. So things like, what are initial masses? How often are they in pairs? How often are they in triples? What are their birth metallicities? And this is important because these initial conditions can have a drastic impact on how the stars evolve. Here's, for instance, an example where metallicity is shown with different colors and lines. And what you see is that what metallicity you start with for the pairs of stars can drastically impact what the total mass of the binary black holes is and how many binary black holes you form in these simulations, as shown here. And so in practice, we not just have to, for instance, try out different hypothetical stars with just 2 different parameters, like 2 different masses. We actually have to explore all these different initial conditions that they can have, often increasing the parameter space already to 10 or 20 dimensions. And so this becomes really, really expensive as we have to explore them all, especially as these sources can really come from cosmological distances where these things are uncertain. The third challenge and hurdle is that these sources are rare. So typically when I run 1,000 binaries in my simulations in my factory, only one of them will form a gravitational wave source. So most of these stars, they will break up when the supernova explosion goes off, because that's such a violent event. And so in practice, this can really lead to Poisson sampling or Poisson uncertainties, meaning that if I have too few gravitational wave sources out of my simulation, then I can't really do any statistics on my data sample, and I get a lot of noise. And so in practice, we have to, again, run our simulations even longer to get enough of these gravitational wave sources in our data set. The fourth and last challenge is that the stellar evolution is very uncertain. And so I already showed you that even in this example where they form from pairs of stars, there's all these different phases like mass transfer, supernovae, a common envelope phase. But all these different phases are still very uncertain. We don't really know how they work and what effects they have with the star. And so in practice, what we do in these codes is that we use parameterized prescriptions where we assign free parameters for all these different phases to kind of explore some of the uncertain physics in those evolutionary stages. And so again, in practice, we have to rerun our entire simulations, changing some of these uncertain physics to have an idea of how they impact our simulation outcomes and the population. And so combined with all these challenges, it means that these simulations become really, really, really computationally expensive. Millions and billions of CPU hours. It takes many, many years to run all of this, and it's just infeasible to do it all. And so current day, everyone who wants to do this pays some price, and usually it means that they don't do at least a few of these barriers and don't explore uncertainties or don't have a significant sample or don't really explore the initial conditions. And so if you were to ask me, what does it often feel like to do gravitational-wave paleontology today, it might look something like this. Where you're just trying to get through all the hurdles, but it's just not really working out. My mom was like, oh, yeah. I think it's a good description of PhD life as well sometimes. And so in my PhD thesis, the goal that I identified is two things. First, I wanted to identify and quantify these uncertainties, these hurdles in these stellar evolution simulations. And then second, I wanted to explore if there are ways to maybe overcome some of these hurdles and address and tackle this uncertainty challenge. Okay, so what did I do? Just like a PhD, not everything is always linear, so this story is going to be a bit less linear than the rest. So the first thing is that I was interested in overcoming this problem that they are rare, and so that they present a rare outcome of simulation. And so actually already during my master thesis, not at Harvard, I found a new algorithm that can speed up these simulations that I call stroopwafel, after the Dutch cookie. And basically how it works is very similar to playing a game of battleships. So in this case, similar to Battleship, you try to locate and resolve as quick as possible the location of your opponent's ships. And in principle, you could do this completely random, like shown here on the left. But in practice, you probably have the tactic here on the right, which is that maybe in the beginning you try random guesses, but then once you find a hit, you want to explore and refine around it. And not only is this a more fun way to actually play the game, not so boring, it actually turns out that you much, much quicker resolve all the locations of the ships around you. And so you more often win the game. So I did something similar for this work, but then implemented it in these stellar evolution simulations. But there's many, many challenges, right? So like these ships, in this case, are the locations in the parameter space. So for instance, the properties of the masses of the stars that form gravitational wave sources, here a hit. But then there's challenging because we don't really know a priori where these locations are going to be, what their size is, how many there are. They're much more rare. And also you have like many, many more dimensions. And so one of the things I did with during my PhD is actually to improve on some of the work that I did as an undergrad and work with two students and Stephen Justin, a professor in Amsterdam, to improve this stroopwafel algorithm to 10 dimensions. And this was especially needed to make sure that the algorithm would still work in higher dimensions, where we kind of made it like more adaptive battleship game tactic, but basically a machine learning tactic. And similarly with collaborators, I worked on further investigating how we can use emulators specifically designed for these weird spaces of stellar evolution where there's many discontinuities to further improve the efficiency of our simulations. These are a lot of technical words, but the only thing you need to remember is that actually by doing this kind of techniques, we could speed up these simulations by a factor of 100. Meaning that now, instead of an entire year, these simulations just take a few days to run. And that's a huge win. And so using these tools in hand, I could now start and have enough computational time to actually explore these other two hurdles, which are the key topic of my PhD. And so, for example, in the first paper and papers, I mostly focused on this. And so for these stellar evolution simulations, you have to remember that there are basically two steps when you do these calculations. So the first step is that you need to find out where and when stars form, so these initial conditions. So how many stars form as a function of redshift, and what are, for instance, their metallicity or masses. And then the second step, for which we use this kind of analytical equations that are based on observations. So for instance here, they're based on galaxies that are mass functions, the star formation rate is a function of time, so this is your Maddow-Dickinson plot, and so on. And these are uncertain, so again, in my simulations, I used 28 variations to explore some of the uncertainties in these assumptions. The second step is that once you form stars as a function of time, you need to also know which of these stars form gravitational wave sources, and how do they form these gravitational wave sources. And so for this, I use COMPASS, but as I mentioned, there's all these uncertain phases. And so in practice, what I did is that I, for instance, studied at least 20 different variations in these uncertainties. Okay. And in this way, I ended up with this large set of simulations that explores both uncertainties in these initial conditions, so the cosmology, as well as the stellar evolution uncertainties. So what does it look like? Well, for my first paper, I explored these two uncertainties and its effect on black hole neutron star mergers. And I focused on black hole neutron star mergers because at the time, they hadn't been observed yet. We'd seen about 10 binary black hole pairs, 1 binary neutron star pair, and then we knew about 20 neutron star pairs from pulsars. But no black hole neutron star system had been observed yet. And so this is one of the most mysterious sources among the three that I decided to focus on. And there was something interesting. So here's some of the results. So on the y-axis, you're now going to see rate. So this is the merger rate. So this basically means how often do black hole neutron stars collide in our universe. So the number of collisions per gigaparsec cube, so per volume, and then per time, per year. And this is something that LIGO can measure. At the time, black hole neutron stars hadn't been observed yet, so LIGO only had this upper limit, this green area. And then I was interested in what these simulations provide. And so one thing that I found is that typically the literature found values that are maybe somewhere here, very low in this diagram. And so it kind of made sense that we maybe hadn't observed them yet, because as you can see, it's kind of far below the upper limit of that line, so maybe we need to just run LIGO much, much longer before we find this. But then I was interested, okay, but what if we explore more of these uncertainties in these simulations? And so I did this. So what you'll now see is that all these different points and lines correspond to these different models and different uncertainties that we explore. So as you go to the right, we cycle through different stellar evolution assumptions, for instance, in mass transfer, common envelope evolution, supernova, and stellar winds. And as you go up, it's basically a simulation that uses different initial conditions, so different cosmology assumptions, like metallicity distributions and star formation rates. And so something that I found is that actually many of these simulations expect many, many more black hole neutron stars compared to kind of the traditional assumption. But moreover, I found that these assumptions and uncertainties, both in the stellar evolution and in cosmology, can drastically impact, for instance, the rate that you expect for these black hole neutron star mergers. And so kind of surprised by this, I decided together with like 3 collaborators to organize a conference that we called Where Are the Black Hole Neutron Star Binaries? Because as my simulation showed, they might be more common, and so maybe we should have seen them already by now. And it just so happened to be that one day before the conference happened, LIGO announced the first 2 observations of black hole neutron star mergers, meaning that this was maybe the most or quickest outdated conference title in a while. I received a lot of emails with requests if maybe next year I could organize like a conference on where is the dark matter or dark energy, which I decided not to do, but. And so based on these 2 detections, which was super exciting and something I think barely happens during a PhD lifetime, I decided also with my advisor, Ido, to write a paper to see if these observations could be explained with these type of models. And so one of the things that we found is shown here, where in blue and orange, you see the properties of the observations, these 2 black hole neutron star mergers, so for instance, their masses and mass ratio. And in gray underlying are my simulation expectations. And your simulations are doing good or can explain the sources if they overlap, which they do here pretty well. And so we concluded that actually the properties and these 2 observations of black hole neutron star mergers can be well explained by the formation of them coming from pairs of isolated massive stars, which was pretty fun. So then I continued this work. I was like pretty excited, like, okay, let's see what happens next. But instead of just focusing on black hole neutron stars, I now focused on all 3 flavors of compact object mergers. So black hole neutron stars, pairs of black hole collisions, and pairs of neutron star collisions. And this is some of the stuff that I found. So this one you already see for black hole neutron stars. Now we actually have, with the 2 observations, an actual error bar, not just an upper limit. And then I did the same for binary black holes, where now you see it's much more flat, which means that actually these assumptions in cosmic evolution are much more impacting the rate compared to the assumptions in stellar evolution. Whereas for binary neutron stars, you see it's very thin, but like goes all around as you move to the right. Meaning that for binary neutron stars, actually the stellar evolution assumptions are much more impacting our expected rates of these sources. And you can explain this because the binary black holes actually behave much differently as a function of birth metallicity. And so here you see as a function of metallicity, the rate or yield of binary black holes goes really down and is steep, whereas for binary neutron stars it's more flat. So this is the reason for, once you're interested in the details, why binary black holes are much more sensitive to your metallicity assumptions and your initial conditions assumptions. This also means, because they're sensitive in different ways, that you could combine the different constraints to further understand and constrain your stellar evolution and cosmic models. So if you want to match all of them with the observed rates, you start ruling out models that you would otherwise not have ruled out if you just looked at a single source. We can do the same trick, but not just for rates, but instead the properties of these sources, such as their masses, which LIGO also measured, where we find very, very similar results. That for binary black holes, they're very sensitive to cosmic history, whereas for instance, black hole neutron stars, they're much more sensitive to the assumptions in your stellar evolution. And so this is good news for us, because on one hand, we do see that expected properties in our simulations are drastically impacted by both these uncertainties. But this is good because since each flavor is impacted in different ways, we might actually use this in the future to really constrain our models and learn something and overcome this uncertainty challenge. For the last chapter in this topic, I was also interested, what about spins? So can we learn additional information from spins, which is also something that LIGO observes? And so I was especially interested in which black hole is spinning. And so with collaborators from Australia, I looked into this picture where maybe intuitively you would think that the more massive star, here MA on the left, eventually evolves first and forms a more massive black hole out of the two stars. Now there's theories out there that maybe the only way to spin up a black hole to make it rapidly rotating is by having the star, only the second formed star, tidally spin up. And so in this case, it means that always only the second formed object is the spinning black hole. So in this case, it would be this smaller black hole that is spinning. However, being in a binary can drastically alter this. So there might be instead, you might start out as these two stars, but now there's mass transfer in between those phases that can actually flip the masses of the stars, meaning that now the second star that initially was less massive ends up being the more massive star. And so in this picture, when you do the same calculation, it's actually the more massive black hole that ends up being the spinning black hole. And so this is something that LIGO can observe. And so we argued that this mass ratio reversal should actually happen in at least 30% of LIGO's binary black holes. And so that which black hole is spinning, if you ask the question to LIGO, can actually inform you about mass transfer phases in the binary evolution, which I think is pretty cool. And we followed this up to see if we could find this in observations, but our main conclusion was that there's not enough data yet to confidently make conclusions about these statements. Okay, so last but not least, we spoke about these uncertainties, but let's go to the fourth challenge, which is that there's also uncertain formation channels, that these formation channels are unknown. And so the first way that I tackled this is to focus on this isolated pairs of stars formation channel. And so there's kind of two formation channels in this way that are usually studied, which is first this traditional one that has a mass transfer phase that's stable, and then an unstable or common envelope phase. But also more recently, people have started to argue that maybe in many cases, actually both of these phases might be stable mass transfer. And so I was curious to study how does this leave imprints in, for instance, these binary black hole simulations. And so what I did is I actually looked and studied several simulations from the literature, as well as from myself, that had different stellar evolution samples, and then asked, okay, for these simulations that at least kind of agree about the total black hole rate, how often do they undergo and include this common envelope? Or how often is it this other channel that is just two stable mass transfer phases? And it turns out that the answer is we don't really know. And so if you look at this figure, then in orange, so on the x-axis, it's like the fraction of binary black holes that either have a common envelope in blue or don't have a common envelope in yellow. And then the other colors are slightly variations of these channels. And what you see is that all these simulations can drastically disagree about whether or not a pair of stars experience a common envelope phase as it forms a binary black hole case. And so this is interesting because on one hand, again, it shows that our simulations still have these many uncertainties, but it also means that if we can somehow constrain or rule out a part of these simulations, that we can more certainly say, okay, this phase happens and actually learn something about this phase from gravitational wave sources. And yeah, but the most important conclusion is that these formation pathways and even intermediate phases can be drastically impacted by, again, these uncertainties. For the last chapter for this topic, I instead went from just isolated binary evolution, so they just come from pairs, to then investigating how does this actually work, what's the picture for all these different formation channels. And so together with Ilya Mandel, we wrote a review paper that shows the expected rate, for instance, of binary black hole mergers for all these different formation channels. So what you now will see is a video that will flip through all these simulations. And what you see on the top, the axis, is like, again, this local black hole merger rate. So how many black holes collide per volume in gigaparsec cube per year. These red lines are the 90% credible intervals from LIGO. So LIGO sees about 100 black holes now. It knows the volume it's sensitive to. And from that, it can infer a rate. And there's 4 rates because they're a little bit uncertain about some of their assumptions. But it lies somewhere between 10 and 100. Now, what happens if you look at these stellar evolution simulations? Then the picture is this. And so now colors are going to correspond to all these different formation channels. So this is, for instance, from pairs of stars. And each horizontal line is one paper, one study from the literature. And so if you pay attention, you're going to see basically 200. You're going to read 200 papers in just a minute. And so for each paper or study, people did this calculation of stellar evolution with their own assumptions and then calculated, for instance, the binary black hole rate. And then maybe they repeated it with some of this uncertain physics. And this gives another scatter point. And then what I did is actually connect all these scatter points with a line to give an idea of the range. And so now you see it for these black hole neutron star mergers. But what you can see is that even for a given study, which again, each study is probably one PhD student like me that sweated throughout their PhD to do these calculations. But you can see that there's drastic uncertainties and that many of these simulations actually range orders of magnitude in possible rates, even between and even within a formation channel. And so this means is that there's these huge uncertainties and that basically on rates alone, by comparing rates alone with the observations, is not enough to, at the moment, rule out certain formation channels. And so importantly, again, I found that the expected merger rate in this case is drastically impacted by uncertainties in both stellar evolution and these initial conditions for all these formation channels, not just for pairs of massive stars. Okay, so back to this picture. I hope I've shown throughout most of this talk that I'm trying to tackle and mostly identify and understand with all these different thesis chapters what these hurdles are, how big they are, and how we might overcome them. And this is important because we're actually in a very, very exciting moment. Namely, we're entering the big data era of these gravitational wave sources, where maybe today we have seen about 100 observations, including the 2 black hole neutron stars mergers. But soon we're actually going to change to this new era where we're going to see many, many observations as new detectors come online with improved sensitivity. So here's a video that, for instance, shows you that maybe today we have about 100, but in the coming years, it's rapidly going to explode to, in the near future, hundreds of thousands of these mergers per year. And the funny thing is that actually even these rates that we might expect, or the number of detections we might expect, is somewhat uncertain. And I wrote a fun paper that actually showed that this is not just one number, but you should add this uncertainty bar here shown in log. But one thing is certain, which is that these future detections in 10 or 20 years are going to completely dwarf the observations that we've seen today. And so this is really, really an incredible time to study gravitational waves, but also their stars. More importantly, not only will we just see more, we're also going to see them much further out and with much higher precision or sensitivity. So today, LIGO can see these black hole collisions basically up to a redshift 1. But these future detectors, like Cosmic Explorer and Einstein Telescope, that are going to be built in about 10 or 20 or 30 years, they're actually going to see these black hole collisions out to redshifts of beyond possibly 100. And so this is insane. Like, we will see, if they exist, black holes that collide before stars were formed. Moreover, we're literally going to see every single black hole merger in our universe that is colliding, which is just, for any astronomer, an amazing population. It's just a complete catalog of these systems. I think something that a lot of other astronomers are jealous of. And so this will be an incredible time to do gravitational-wave paleontology, but of course it will require to really overcome all these barriers and get ready to use this huge amount of data to learn about the stars and their lives. And so I really hope that with my work we can go from this left picture to, at least within 10 or 20 years, to this right picture where we're kind of understanding and have trained ourselves to overcome all these hurdles, and hopefully in 20 years are almost flying over them, maybe not this simple. And can really, really start to understand and model how these stars evolve, which will allow us to do gravitational-wave paleontology, allow us to study these massive stars that will then allow us to really answer many of these open questions in astronomy today about all these different processes in our universe. Now, in the last minute, basically, I only want to say that in my last chapter, I also do one more thing, which is that I also address how uncertainties are not just common in these simulations, but also actually in the lives of scientists. And for instance, we know that underrepresented minorities, and especially multiple marginalized minorities, such as women of color, can actually experience many more of these barriers, in their academic careers, which includes harassment. And so in my last chapter, I actually, very quickly, 2-page, have recommend 10 ways that I think any astronomy department, just like CFA, can improve support for people like me and other early career astronomers to have a better support system for people to hopefully fly through their PhD. There's many here, but 2 I want to highlight is that having a code of ethics is really helpful, and I'm really glad that also Lisa is soon publishing that on their CFA, but also just connecting members with the local resources out there so that people know where to find the support and where to go to find this. And as Ido said, I'm actually really, really happy, and one of the maybe most fun parts was actually to help improve some of these support systems throughout my PhD. That being said, I also want to acknowledge many of the support that I've gotten from many of you here. So first of all, Ido and his research group, really fun over all the many past years, and including former members who are not mentioned here. One thing you should know about Ido, there's a lot of things I can tell about him, but one thing you should know is that, one thing that might happen is that one day I will walk in his office and I'll be like, hey Ido, shall we organize a gravitational-wave conference in 3 weeks or so? And so most advisors at this point will be like, you still have 3 unfinished papers, 2 courses, I don't know, it's a lot of waste of time, I don't know, no. Ido on the other end, he's like, yeah, sure, why not? Sounds fun. And this has happened many, many times. And so what happens is that you organize a gravitational-wave conference in this room, which ends up being really fun. And so, there's 100 other examples that I can give, but I really think that, this is one example of something that has really allowed me to explore my own creativity, also make my own mistakes, many of which I did, but really learned from that, and I really appreciate that you always trusted in me. I want to mention all the awesome students I got to work with during my PhD. I think Adam is here, yeah. And also, if you want to work with me in the future, please do. I'll be looking for students in some near future. The Compass collaboration has been an amazing resource and community, many of them who are here, that I cannot thank enough, especially Lika. Oh my gosh, I cannot. Words cannot describe how much time we spent together on everything, but I appreciate you. Many of the mentors, faculty who have helped me both in my undergrad, but also here with stupid questions, with good questions. But yeah, I really appreciate everyone's support, as well as like many of the people, including Peg and others. Lisa, I can never find a picture of you. But there's really many people who have always helped, like who've always like helped improve the environment, but also just like join me in my crazy idea. I want to do a special shout out to Mariah Silver, who's now at MIT, Christina Ritchie, and Marisa Boragina, who have provided a lot of support in many ways. Then I just thought there's no way I can do justice in acknowledging all my friends, but I just wanted to give you like a glimpse of what a PhD at Harvard also looks like, other than research. So the first one is that kayaking, great pandemic activity because it's kind of like distant. So if I haven't taken out kayaking on the Charles yet, please let me know. I still have some time and some single passes, which include Doug Finkbeiner, who is my committee chair, and at some point we moved the committee, our meetings to the kayak, so that was pretty fun. The same can be said about hiking, for which I always have the best friends and also roommates to join me. The other famous thing is volleyball, including that we once had a faculty versus student volleyball match, which we lost. To my surprise, because we had trained for a year to beat them. And I still get emails today sometimes from faculty like, oh, I still cannot. Such a surprise that we won, right? And I was like, yeah. So I want to do a rematch before we leave. Also juggling, which has also been a great pandemic activity, actually. It's a good, you can only do it for 50 minutes and then you're sick of it, so it's a good break moment. And all the like crazy science, such as like Claire Lemon making this crazy gravitational-wave cake, but then of merging alpacas, in case you don't recognize it. And I once went to Halloween with dressed as like Lego's graveyard. I won a prize, you can laugh, but I won a prize, so it was pretty fun. As well as like all the crazy running that we did, including my first marathon in Rome, which was pretty fun. Anyways, there's way too much. I was like, oh, I should like, whatever, tell the people, but there's just like, I will talk to people one-on-one because there's just like no way to even start like addressing how much I appreciate you. And a lot of random photos. I just want to end to also thank my family. I'm not going to cry, hopefully. But Luz, Bram, you're amazing. I'm so proud of you. And you always support me. And Mama and Papa, I love you. And you're always supportive, even if I move across the country, across the water, and you hate that. Yeah, I know you've gone through a lot of challenges in the past years, but I'm really happy you're here. And I'm so proud of you and happy for all your unconditional love. With that said, I'll leave you with my conclusions and we'll say thank you.
We have time for questions. Yes.
Thank you, Floor. I don't know anything about this topic, and I now feel like I know a lot. So, in the conference that you organized when you published the first detection the day before, what kind of constraints did that place in what you thought before that came out?
Yeah, no, that's a good question. So the question was like, once the Black Hole Neutron Star observations came out, like what kind of constraints did it give? It was actually funny because when we organized the conference, so it happened the day before, so I actually heard that like all the presenters had to like slightly change their presentation slide to like include like the constraints of these new observations, which was interesting. But I think I learned a lot. So one of the things is that it turns out that these black hole neutron stars are indeed more common than maybe people thought. And so this is actually challenging to make that many black hole mergers with some of these other formation channels. So whereas these binary black holes and binary neutron stars, they can, for instance, be produced in high rates in, for instance, these dense dynamical environments like globular clusters, it's really hard to make this many black hole neutron stars in these dense environments, because typically what happens is that you either sink the black holes and you can make a black hole collisions, or you sink the neutron stars and you can make a lot of neutron star collisions. But if you sink both black holes and neutron stars to the core, typically what happens is that the neutron stars get kicked out and you leave the more massive black holes in the interactions. And so you would never get these high black hole neutron star rates as we now found. So the fact that we've seen 2, maybe 4 actually by now, probably means that they must come from pairs of massive stars, which is very interesting, because if they come from pairs of massive stars, then why not a lot of the others, like binary neutron stars and binary black holes? Yeah.
Yeah, I also don't know a lot about the topic, but I was wondering, because you showed the 4 hurdles, of course, which you also researched. Are they really the same heights, or is one way more challenging than the others?
That's a good one. Are there different heights? That's a good question. I think these uncertainties here are the biggest hurdle heights. I think formation channels, there's already some ways that we can start to at least somewhat constrain them. I think these uncertainties in stellar evolutions and initial conditions, it's just really hard to constrain it in any other way. So we really have to rely on our modeling, having trust in our modeling to be good enough that we can at some point overcome them. Whereas I think this is okay, you just run your simulations really long, and formation channels is kind of there's some other constraints where you can start to say, okay, it must be, for instance, from pairs of massive stars. So I think, the other two are probably really high.
I have a question.
They're all amazing.
So, there's this gravitational wave revolution that's coming, hopefully in the next
Yes.
decade or two. We're going to see the entire universe. But there are other big things happening in astronomy. So JWST is giving us a view of early galaxies. We're going to have the Rubin Observatory LSST survey finding millions of supernovae. How do you see this playing into what you're trying to do?
Yeah, no, that's a good question. I have some backup slides also too. We can discuss that in the closed meeting too. But I think it's going to be very, very important, because I think this challenge is really difficult, and especially to get better constraints on these uncertain stellar evolution and initial conditions. It will really help to use additional observations, which include LSST, which will see a lot of supernovae, kilonovae, maybe red novae that can further help understand some of these phases. Gaia, that might and has already seen a few black hole star binaries that tells us a lot about how black holes form in our own Milky Way, as well as even surveys like LISA that will look at frequencies or gravitational waves at a different frequency and might see these double compact object mergers in our own Milky Way backyard. So I think each of these should in the future be combined to help us constrain especially these uncertain conditions. Mm-hmm. Emily.
When you show all these different models, is there a reason to think that they're mutually exclusive, or could the reality be that some are following certain pathways and others are following other pathways, and it's not it's a combination of everything?
Yeah. So the question is more than one formation channel at play? Yeah. So most likely there is. There's even already some evidence from gravitational wave data that there might be at least a few different formation channels at play. For example, there's kind of an agreement that these pairs of massive stars have a really hard time forming very massive black holes and forming black hole mergers with opposite spin, basically. And so we have some evidence that there are at least a small fraction of black hole mergers have those properties. And thus that maybe say 10 or 20% of the mergers might actually form from dynamical interactions. And so this makes it more of a challenge, because we should truly start modeling them all. Which is one of my future projects that I want to work on. But it's, so there is evidence, but there's still hope that maybe we can even, from observations, identify, say this 80% comes from this channel, this 20% has the same properties, and still use that in some way.
Yes.
Would finding a white dwarf merger help constrain your models, or is that probably a completely different mass range?
Yeah, I mean, in some ways it does, because some process will be the same, right? So whether stars, how they like to pair up, and like if these white dwarf mergers can help constrain things like mass transfer, it will. But there's definitely, since they come from lower mass stars typically, there's definitely a lot of physics that might behave very differently. So the hope is that we can use it. The question is really how, and I think that requires a few more PhD theses in the future before we figure that out. Yeah.
So Floor, wonderful talk and wonderful thesis, which we're going to discuss shortly. What is the biggest uncertainty in stellar evolution in your mind? I've got some candidates, so I'm going to let you answer.
The funny thing is, that's like maybe one of the most common questions we get. I would say, no, this is a great question. And it's hard to answer because I think the true answer is we don't entirely know. But one of my current answers would be the common envelope phase that we think like brings these black holes and neutron stars really, really close together. And so the funny thing is, if you actually were to open our code, like Compass, it looks something like this. It's like a simple equation that's like, okay, you have some masses, some separation, some final separation, and on the left, like some other masses, and then this alpha and lambda are these two free parameters. And this whole equation, which only has like two free parameters, decides how much they shrink, how easy it is to eject this envelope, and whether you survive. And this has a drastic impact on like how many black holes collide, but also what the properties are. In practice, and this again, this is like one equation, two free parameters. In practice, it probably looks something more like this, and this is a hydro simulation of that phase, where you can see there's a lot of extra dimension, like gas, there's like lots happening, and lots of physics happening, and even this is 2D, and so it's not even, it should probably even be more complicated than this. And so I think this is one of those phases that's most unconstrained, and there's even people here, like Magda, for instance, working on, how our simple assumptions, might actually not be so realistic to do this kind of stellar evolution that includes a lot of gas and dirty physics. Mm-hmm.
Okay, with dirty physics, I think we're going to call it here.
Oh no!
And thank you for